Scharfen. Tonight, there is a truth waiting for you. A truth that most people are not prepared to face. One that an entire century of science fiction has worked tirelessly to conceal. One that dismantles the grandest dream our civilization has ever dared to hold. We will never travel among the stars. Not in your lifetime. Not in the lifetime of your children, or their children's children, or in 1,000 generations of children yet to come. The stars are not a destination we are moving toward. They are a horizon that retreats with every step we take, separated from us by distances so incomprehensible and by barriers so deeply embedded in the laws of nature that no accumulation of human ingenuity will ever bridge them. By the time this journey ends, you will understand precisely why the dream of standing on a world orbiting a distant sun, of setting foot on alien soil beneath an alien sky, is something that will remain permanently and irrevocably a dream. Before we go any further, if you find yourself drawn to questions like this one, questions that strip away the comfortable stories and force you to see the universe as it actually is, consider subscribing and leaving a like. It costs you nothing, and it allows this channel to keep exploring the deepest and most difficult corners of what we know. Now, settle in, make yourself comfortable. Let's begin. There is a comparison that gets made constantly, in classrooms, in documentaries, in the speeches of space agency directors and billionaire visionaries. The comparison goes like this. Traveling to the stars is like crossing the ocean. It is dangerous, yes. It is difficult, certainly. But humans crossed oceans. Humans explored continents. Humans walked to the poles and climbed to the summits of the highest mountains on Earth. And so, given enough time, given enough determination, we will cross this ocean too. It is a beautiful comparison. It is also completely wrong. When European vessels first pushed west across the Atlantic in the 15th century, the crossing was brutal. Ships were small and fragile. Scurvy claimed lives. Storms claimed more. Many vessels never returned, but the journey was survivable with the technology of the era. Sailors could carry enough food and water. They could fish along the way. They could navigate by the stars. The crossing took weeks, sometimes months, but a human body could endure it. When Polynesian navigators spread across the Pacific millennia earlier, threading from island chain to island chain across tens of thousands of miles of open ocean in outrigger canoes, they were performing one of the most extraordinary feats of human exploration in history. But islands existed. Stopping points existed. A canoe could carry enough provisions to reach the next landfall. Even Antarctica, one of the most hostile surfaces our planet offers, a place where the wind can freeze exposed skin in minutes, and where the nearest help is hundreds of miles away, even Antarctica can be crossed. Explorers have done it on foot. It requires precise planning, specialized equipment, enormous physical endurance, but a human being can walk across it and survive. Space between the stars is not like any of these places. There are no islands, there are no stopping points, there is no fish to catch, no fresh water to collect, no ground to rest on. There is only vacuum, perfect, absolute, lethal vacuum stretching across distances that make the entire history of human exploration look like a child's first steps across a living room floor. To understand what you are actually confronting when you talk about interstellar travel, try to hold this image in your mind. Imagine the Atlantic Ocean is not 3,000 miles wide, but 30 trillion miles wide. And instead of water, it is filled with radiation energetic enough to destroy human cells. And there is no atmosphere, so breathing is not possible. And the temperature in shadow sits just a few degrees above the coldest anything can ever be. And in direct sunlight, exposed surfaces reach temperatures that would vaporize metal. And there is no life of any kind, no current to carry you, no wind to fill your sails, no biological system of any sort to sustain you. And your ship cannot carry enough provisions to survive the crossing. And even if it could, even if you solved every single one of those problems, you would grow old and die long before you reach the other side. That is what traveling between stars actually means. The nearest star to Earth, setting aside our own sun, is a dim red dwarf called Proxima Centauri. It belongs to a triple star system, the Alpha Centauri system, which represents our closest stellar neighbor in the entire cosmos. Proxima Centauri sits at a distance of 4.24 light-years. That is the distance that light itself, moving at 186,282 miles every single second, covers in 4 years and 3 months. Light is not merely fast. Light is the fastest thing that exists, or can exist in this universe. Its speed is not a record waiting to be broken. It is a boundary woven into the fabric of space-time, a hard limit imposed by the deepest structure of physical reality. And even at that ultimate speed, it takes light more than 4 years to reach our nearest neighbor. Now let the distance resolve into something your mind can hold. 4.24 light-years is approximately 25 trillion miles. 25 followed by 12 zeros. The number itself is almost meaningless without context, so consider this. The circumference of Earth at the equator is roughly 24,900 miles. If you wanted to stack Earth's circumferences end to end until they reached Proxima Centauri, you would need approximately 1 billion of them. 1,000 million times around the entire planet. That is the gap between us and the closest star. Or consider time. Light travels so fast that in a single second, it can circle the Earth more than 7 times. At that speed, a beam of light aimed at Proxima Centauri right now at this exact moment would not arrive until the year 2030. And if that beam bounced back to us instantly, we would not see the reflection until 2034. 8 years round trip for the fastest thing in the universe. Now scale that to human travel. The distance from Earth to the Moon, the journey that required the most powerful rockets ever constructed, the journey that took Apollo astronauts 3 days, is roughly 239,000 miles. Proxima Centauri is approximately 105 billion times farther than the Moon. The distance to Mars, which NASA has been working towards sending humans to for decades, ranges from about 35 million miles at closest approach to over 250 million miles when both planets sit on opposite sides of the Sunday. A crewed mission to Mars using current propulsion technology would take somewhere between 6 and 9 months just to get there. 6 to 9 months to travel tens of millions of miles. Proxima Centauri is 25 trillion miles away. At the speed a Mars mission would travel roughly 35,000 miles per hour, accounting for the orbital mechanics required to actually intercept the planet reaching Proxima Centauri, would take approximately 81,000 years. 81,000 years. When that journey began, our ancestors were painting animals on cave walls. Agriculture had not yet been invented. The wheel did not exist. The entirety of recorded human history, every empire, every war, every scientific revolution, every work of art and philosophy and literature that civilization has produced would fit inside the travel time remaining after those 81,000 years had elapsed. And yet, Proxima Centauri is our closest neighbor. Of the hundreds of billions of stars in our galaxy, it is the one sitting right next door. At this point, you may be thinking what anyone raised on the trajectory of human technological progress naturally thinks. We are not confined to current technology. The Wright brothers flew 120 feet in 1903, and 66 years later, human beings walked on the moon. Progress is real. Progress is dramatic. We will build faster ships. And you are right that progress is real. But what lies ahead are not engineering problems waiting for clever solutions. What lies ahead are walls built from the laws of physics themselves. Consider the fastest object humans have ever created. The Parker Solar Probe, launched in 2018 and designed to pass through the Sun's outer atmosphere on repeated close approaches, uses gravity assists from Venus to reach extraordinary velocities. At its peak, the Parker Solar Probe travels at roughly 430,000 miles per hour. That is approximately 0.064% of the speed of light. It is fast enough to travel from New York to Los Angeles in about 20 seconds. Fast enough to circle the entire Earth in under 3 minutes. At that speed, traveling continuously without stopping, the journey to Proxima Centauri would take over 6,700 years. When that voyage began, The first Egyptian dynasty was just being established. The pyramids had not yet been built. The Bronze Age had barely begun. All of Greek philosophy, all of Roman history, the rise of every major world religion, the Renaissance, the scientific revolution, the industrial revolution, both world wars, the entire digital age, all of it would occur within the travel time remaining. And the Parker Solar Probe was not designed for interstellar travel. It was designed to study the Sunday. So let us consider what a spacecraft actually designed for speed might achieve. Breakthrough Starshot is a project backed by some of the most serious names in science and technology, including the late Stephen Hawking and investor Yuri Milner. The proposal is elegant in its simplicity. Build spacecraft so small and so light that the tyranny of the rocket equation becomes irrelevant. Equip them with reflective sails. Then strike those sails with pulses of laser light so powerful that the pressure of photons alone accelerates the craft to a significant fraction of light speed. The target velocity is 20% of the speed of light. At that pace, a probe would reach the Alpha Centauri system in roughly 20 years. 20 years. That sounds, for the first time in this conversation, like something a human being could relate to. A journey lasting 20 years is long, but it is not geological. It is not civilizational. A person who launched such a probe at 30 years old might still be alive to see it arrive. But here is what Breakthrough Starshot actually involves when you examine the specifics. The spacecraft would weigh approximately 1 gram. That is the mass of a single paperclip, 1 gram including every scientific instrument, every communication system, every power source, every component required to gather data in another star system and transmit it back across 4.24 light-years to receivers on Earth. The laser array needed to accelerate this paperclip to 20% of light speed would need to generate approximately 100 gigawatts of power during the launch burn. 100 gigawatts is roughly equivalent to the combined output of 100 nuclear power plants, all focused into a single coherent beam aimed at a target the size of a thumbnail. The engineering obstacles are not trivial. Keeping a laser of that magnitude locked onto a tiny accelerating sail over the duration of the burn, building a sail that can absorb that intensity of radiation without vaporizing, miniaturizing functional scientific instruments, and a radio transmitter capable of reaching Earth across interstellar distances into a package massing 1 gram. These challenges sit at the absolute frontier of what physics might permit, even with perfect engineering. And even if every one of those challenges was solved, even if Breakthrough Starshot succeeded beyond all expectations, what you would have is a flyby. The probe would scream through the Alpha Centauri system at 20% of light speed, spending a matter of hours in the vicinity of those stars before continuing onward into the permanent darkness of interstellar space. It cannot slow down. At that velocity, there is no way to decelerate. No fuel supply that could physically fit aboard a 1 gram craft could generate the thrust needed to shed that speed. The probe arrives, glimpses, and vanishes forever. That is the absolute ceiling of what current scientific proposals can offer. A paperclip-sized robot on a one-way flyby mission. Now we must talk about sending human beings, because the dream, the actual dream that has animated a century of science fiction and shaped the deepest aspirations of our species, is not about sending paperclip robots on glorified drive-bys. It is about people. It is about explorers standing on alien worlds, breathing alien air, looking up at an unfamiliar sky. It is about colonies and civilizations and the expansion of humanity beyond this single fragile world. That is what people mean when they say we will one day travel among the stars. And it is here that physics becomes not merely challenging but crushing. Begin with the most basic constraint, energy. To move any object, you must supply energy proportional to its mass and the square of its desired velocity. This relationship, kinetic energy equals 1/2 times mass times velocity squared, is one of the most fundamental equations in all of physics. It contains no ambiguity and admits no exceptions. And when you apply it to the problem of accelerating a spacecraft capable of sustaining human life across interstellar distances, The numbers that emerge are staggering in a way that resists casual comprehension. First, consider the mass of such a ship. The International Space Station supports a crew of 6 to 7 people, requires resupply from Earth every few months, cannot travel anywhere under its own power, and has a total mass of approximately 420,000 kilograms. A vessel genuinely designed for interstellar human travel would need to do everything the ISS does, and then vastly more. It would need air recycling systems capable of functioning without resupply for decades, water purification and recirculation systems, food production infrastructure, likely full hydroponic agricultural chambers capable of feeding the crew indefinitely, medical facilities, including surgical capability, living quarters, common spaces, exercise facilities to counteract the physiological deterioration of long-duration microgravity, power generation systems, almost certainly multiple nuclear reactors for redundancy, radiation shielding massive enough to meaningfully reduce cosmic ray exposure, structural integrity to withstand decades of operation and the stresses of acceleration and deceleration, spare parts, fabrication equipment, machine shops capable of manufacturing replacements for any component that fails, backup systems for every critical function, because in interstellar space there is no rescue mission and no resupply. Conservative estimates for such a vessel begin at around 10 million kilograms. More realistic assessments, accounting for genuine long-term self-sufficiency and appropriate redundancy, push toward 50 to 100 million kilograms. Let us use 100 million kilograms, 100,000 metric tons, roughly the displacement of a large modern aircraft carrier, as our working figure. Now we want to accelerate this ship to 10% of the speed of light, not 20%, not 50, a modest 10%, which would still require over 40 years just to reach Proxima Centauri. 10% of light speed is approximately 30,000 kilometers per second. Inserting these values into the kinetic energy equation, 1/2 multiplied by 100 million kilograms multiplied by 30 million meters per second squared. The result is approximately 4.5 times 10 to the power of 23 joules. That number needs context to mean anything. The total annual energy consumption of all human civilization, every power plant on every continent, every vehicle burning every gallon of fuel, every light bulb and data center and factory on Earth combined amounts to roughly 5.8 times 10 to the power of 20 joules per year. The energy required to accelerate our interstellar ship to 10% of light speed is approximately 775 times that figure. 3/4 of a millennium worth of all human energy production consumed in a single acceleration burn. And that is only the outbound journey. When the ship arrives at its destination, it must decelerate. Otherwise, it simply streaks past the target star system at 10% of light speed, which renders the entire exercise meaningless. Deceleration requires the same energy as acceleration, so the true figure doubles, something approaching 1,550 times the total annual energy output of all human civilization for a single voyage to the nearest star. Where does this energy come from? It must either be carried aboard the vessel or beamed from an external source. And here is where the rocket equation, formulated by the Russian mathematician Konstantin Tsiolkovsky in the early 20th century, introduces a cruelty that cannot be engineered around. The rocket equation describes the relationship between a spacecraft's achievable velocity change, the exhaust velocity of its propellant, and the ratio of its fueled mass to its empty mass. The mathematics are unambiguous. To achieve very high velocity changes, the required fuel mass grows exponentially. Not linearly, exponentially. Double the desired velocity, and the fuel requirement does not double. It increases by a factor that can be many times larger, depending on the exhaust velocity of your propellant. For chemical rockets, the kind that have launched every crewed spacecraft in history, from Yuri Gagarin's Vostok to the Saturn V that carried humans to the moon, the exhaust velocity is constrained by the chemistry of combustion. The best chemical propellants achieve exhaust velocities of roughly 4 to 5 kilometers per second. To reach 30,000 kilometers per second using chemical propulsion, The mathematics produce a mass ratio so extreme that the required fuel would outweigh not just the ship, but planets. It is not an engineering problem, it is a mathematical impossibility. Nuclear fission splitting heavy atomic nuclei, such as uranium or plutonium, releases millions of times more energy per kilogram than chemical combustion. Nuclear fusion, the process that powers the sun by fusing light nuclei such as hydrogen isotopes, releases even more. In the 1970s, the British Interplanetary Society conducted a detailed study called Project Daedalus, designing a theoretical unmanned probe to reach Barnard's star approximately 6 light-years away, using helium-3 and deuterium fusion propulsion. The probe would accelerate to roughly 12% of light speed, arriving in approximately 50 years. The fuel requirements were extraordinary. The spacecraft would need to carry approximately 50,000 tons of fusion propellant. Its initial total mass, including that fuel load, exceeded 54,000 tons, and this was for an unmanned probe with a final payload of only a few tons. Scaling to a crewed vessel of 100,000 tons would require fuel masses measured in the millions of tons, and helium-3, one of the required fuels, is essentially non-existent on Earth. It would need to be mined from the atmospheres of Jupiter or Saturn, or extracted from lunar regolith, requiring an industrial infrastructure that does not currently exist and would take decades to construct. And we do not yet have working fusion reactors. After 6 decades of research, controlled nuclear fusion for power generation remains elusive. Experiments like ITER represent genuine progress, but practical fusion technology is still years away at minimum, and a compact, high-thrust fusion drive capable of propelling an interstellar vessel is a technology several orders of magnitude more demanding than a stationary power plant. Then there is antimatter. When matter and antimatter meet, they annihilate completely, converting 100% of their combined mass directly into energy, according to Einstein's equation relating energy, mass, and the speed of light. No other physical process extracts energy from mass more efficiently. Nuclear fission converts roughly 0.1% of mass into energy. Nuclear fusion converts about 0.7%. Antimatter annihilation converts the full 100%. It is the theoretical upper limit of energy density. A single kilogram of antimatter annihilating against a kilogram of ordinary matter would release energy equivalent to roughly 43 megatons of explosive yield. The atomic bomb dropped on Hiroshima released approximately 15 kilotons. 2 kilograms of fuel, 1 matter, 1 antimatter, would release energy equivalent to nearly 3,000 Hiroshima bombs. If that energy could be efficiently channeled into thrust, calculations suggest an antimatter-powered spacecraft might reach 30 to 50% of light speed. At 50%, the journey to Proxima Centauri would take approximately 8.5 years. For the first time in this conversation, we have a travel time that a human being could survive a journey lasting roughly as long as some historical ocean voyages of exploration. But here is the reality of antimatter. It does not occur naturally anywhere we can access. The universe is composed overwhelmingly of ordinary matter. Antimatter particles are produced in high-energy collisions, particle accelerators, cosmic ray events near black holes, but they annihilate almost instantaneously upon contact with the ordinary matter that fills everything around them. To use antimatter as fuel, we must manufacture it. We create antimatter in particle accelerators by colliding high-energy particles and occasionally producing matter-antimatter pairs. The process is spectacularly inefficient. Current accelerators consume roughly 10 billion times more energy than the annihilation energy the resulting antimatter would release. 10 billion times more energy in than energy out. The total quantity of antimatter produced by every particle accelerator in human history, added together across all facilities and all years of operation, is measured in nanograms billionths of a gram, less than the mass of a grain of dust. CERN's facilities produce approximately 10 million antiprotons per minute during operation. Each antiproton has a mass of 1.67 times 10 to the power of -27 kilograms. 10 million antiprotons have a combined mass of roughly 1.67 times 10 to the power of negative 20 kilograms. Running CERN continuously for an entire year would yield approximately 9 trillionths of a kilogram of antimatter. To accumulate a single gram at that rate would require over 100 million years of uninterrupted operation. And storage presents its own impossible challenge. Antimatter annihilates the instant it contacts ordinary matter, which means the walls of any container, the air, any physical surface at all. The only way to store it is suspended within electromagnetic fields inside a perfect vacuum, a device called a penning trap. CERN has successfully stored antiprotons for over a year using such traps. But the quantities involved are vanishingly small, hundreds of thousands of particles at most, and the traps require continuous power to maintain the confining fields. A momentary power interruption and the antimatter drifts into the walls and detonates. Scaling this to the tons of antimatter needed for an interstellar mission and then keeping that fuel stable inside a spacecraft for decades of travel presents challenges that may be physically insurmountable. You would essentially be flying through space with a continuously armed explosive device of unimaginable destructive potential, held in check only by electromagnetic systems that must never, under any circumstance, experience even a momentary failure. Even setting aside production and storage, the engineering of an antimatter engine remains entirely theoretical. When matter and antimatter annihilate, they produce gamma rays and subatomic particles called pions. Approximately 40% of the annihilation energy is carried away by neutrinos, particles that interact so weakly with matter that they pass straight through the spacecraft and vanish into space, irretrievably lost. You cannot capture neutrino energy, it is gone. So before the engine even begins, 40% of the fuel's theoretical yield has already escaped, unavoidably, by the laws of physics. The gamma rays and charged particles that remain can theoretically be directed using magnetic fields to produce thrust. But gamma rays do not respond to magnetic fields. Containing and directing them requires massive physical structures, shielding material to absorb and convert the radiation, which adds mass, which requires more fuel to accelerate, which requires more antimatter, which cannot be produced. Nobody has ever built an antimatter rocket engine, not even a laboratory prototype. We do not know with certainty that it is possible to extract meaningful thrust from annihilation reactions. The concept exists on paper, in equations, in theoretical studies. It has never been tested in any form. So the energy problem stands. Chemical propulsion is mathematically impossible at interstellar scales. Nuclear fission and fusion offer genuine improvements, but still fall far short of what is needed, and fusion technology does not yet exist in practical form. Antimatter offers the highest theoretical energy density physically permitted, but cannot be produced, stored, or used with any technology we possess or can clearly envision, and every approach still confronts the same fundamental arithmetic. Moving massive objects across interstellar distances requires energy on a scale that strains the imagination and defeats every propulsion concept currently within our reach. These are not obstacles that patience and ingenuity will dissolve. They are walls built from the equations that govern reality itself. 8:45. Let us set aside propulsion for a moment and grant an assumption we have not earned. Let us imagine that somehow, through some breakthrough we cannot currently envision, we solve the energy problem. We build a ship capable of traveling at 10% of light speed. The journey to Proxima Centauri takes 42 years. To a star 10 light-years away, over a century. To the more distant stars that populate the majority of our galaxy, centuries or millennia. What happens to the people inside? This is where the conversation shifts from physics to something more intimate and in some ways more devastating, because the barriers here are not imposed by equations, they are imposed by what we are, by the particular kind of creature that evolution spent 4 billion years assembling on the surface of this planet. A human life, even a long and fortunate one, spans roughly 70 to 80 years. If you launched a ship toward Proxima Centauri at 10% of light speed and the journey took 42 years, a crew member who departed at the age of 25 would arrive at 67 if they survived. They would spend the entirety of their adult lives in transit, never touching a planetary surface, never breathing unrecycled air, never feeling gravity that was not mechanically generated, never seeing a sky. They would arrive elderly at a destination they had spent their entire conscious lives traveling toward, with whatever remained of their health and vitality, to begin the work of establishing a presence in an utterly alien star system. For any star beyond Proxima Centauri, no one who departed would survive to arrive. The journey would outlast its crew. This is the premise of the generation ship, a vessel large enough and self-sufficient enough to sustain a stable human population, not for one lifetime, but for many. The crew would not merely travel to another star. They would live and die aboard the ship. Their children would be born in space, grow up in space, age and die in space. Perhaps their grandchildren or their great-grandchildren would be the ones who finally decelerated into orbit around a distant sun. Generations of human beings who never knew Earth except as a story, a recording, a legend. The concept has a kind of epic grandeur to it when considered in the abstract. But when you examine it carefully, when you actually think through what it would require of human beings as they actually are, not as we might wish them to be, the difficulties accumulate into something that looks very much like impossibility. Begin with governance. A generation ship is a closed system. There is no outside. There is no frontier to retreat to, no neighboring territory to migrate toward if internal tensions become unbearable, no authority beyond the hull. Whatever political structure exists aboard the ship is the only political structure that exists for those people, and it must function without catastrophic failure for not years or decades, but potentially centuries. Consider the options. A democratic system in which the population governs itself through collective decision-making sounds appealing. It reflects values that many of us hold deeply. But democracy requires that losing factions accept outcomes they oppose. On Earth, dissatisfied minorities have recourse. They can organize, protest, form separatist communities, emigrate, express dissent through art and culture and political agitation over time. On a generation ship, a faction that loses a critical vote and feels strongly enough about the outcome has only one meaningful form of recourse: sabotage. A determined minority with access to life support systems, propulsion controls, or the reactor could hold the entire vessel hostage. The vulnerability of a closed technological ecosystem to internal disruption is absolute. An authoritarian system might maintain order more effectively, but it generates the resentment and psychological damage that authoritarianism always generates, concentrated in a space from which no one can escape. And authoritarian systems are acutely vulnerable to succession crises. The death of a strong central leader has ignited civil conflict repeatedly throughout human history, in societies with far more room to absorb the resulting chaos than a metal cylinder traveling through interstellar space. There is also the problem of mission continuity across generations. The original crew chose to go. They believed in the mission with the conviction required to leave Earth forever, to commit their entire lives to a journey they would not survive, to raise children who would inherit an obligation they never chose. But those children did not choose. Their children's children did not choose. By the fourth or fifth generation, the original mission reached that star, established that colony. Carry humanity beyond its home system is an abstraction, a story told by dead people about a destination no living person has ever seen. What if they vote to turn around? What if 4 generations into the voyage, the population decides collectively that they want to go back? The journey home would take just as long as the journey out. Earth would have changed beyond recognition. But the impulse is entirely human and entirely predictable. People tend to value the concrete and familiar over the abstract and distant. A destination star is a concept. Home, or the idea of home, is something else entirely. Can you ethically bind unborn generations to a course of action decided by their ancestors? Can you design a social structure that prevents future populations from exercising sovereignty over their own trajectory? And if you build in mechanisms to prevent that, if you create a system where the mission cannot be abandoned regardless of the wishes of the living, you have created something closer to a prison than a civilization. Then there is the psychological dimension. Human beings evolved over hundreds of thousands of years in a particular kind of environment. Open landscapes, changing weather, seasons, the smell of rain and soil and vegetation, natural light cycling through dawn and dusk, and the gradations between. Social groups of roughly 50 to 150 individuals embedded in landscapes that offered genuine physical variation. Our nervous systems were shaped by that environment. Our sense of well-being, our emotional regulation, our fundamental experience of being alive, all of it calibrated to a world that a generation ship cannot provide. Studies of people who spend extended periods in confined, isolated environments, researchers at Antarctic stations, crews aboard submarines, participants in isolation experiments consistently document the same pattern. Initial adjustment, followed by what researchers call the winter over syndrome, or the third quarter phenomenon. Irritability, depression, interpersonal conflict, difficulty concentrating, a pervasive sense of meaninglessness. These effects emerge after months, sometimes weeks. The assignments last a year at most, occasionally 2, and the subjects know they will return to the open world when they end. What happens over a lifetime? What happens over 3 lifetimes? In a metal corridor that smells of recycled air and machinery, under lighting that approximates the sun but is not the sun, with a sky that is a ceiling and a horizon that is a wall. The psychological consequences are genuinely unknown because nothing like this has ever been attempted. But everything we understand about human psychology suggests they would be severe and that they would compound across generations as the memory of the open world faded and the confinement became the only reality anyone had ever known. Mental health problems in a closed population are not individual misfortunes, they are systemic risks. Depression spreads through social networks, anxiety disorders cluster in families, trauma echoes across generations. A population under sustained psychological stress makes worse decisions, maintains social cohesion less effectively, generates more interpersonal conflict. And in an environment where interpersonal conflict cannot be escaped, and where every individual is critical to the functioning of the whole, the consequences cascade. Biological constraints impose their own pressures. A genetically healthy population requires diversity. Without it, harmful recessive traits become increasingly expressed with each generation. Fertility declines, susceptibility to disease increases, and the long-term viability of the population degrades. Population geneticists estimate that maintaining healthy genetic diversity across many generations in a closed population requires a minimum founding group of several hundred individuals. Some estimates suggest closer to 1,000 or more, with mating patterns distributed broadly enough to prevent the concentration of harmful alleles. But human beings do not select partners according to population genetics. We select partners based on attraction, proximity, shared experience, emotional resonance. The mating patterns that result from genuine human choice tend to cluster in ways that accelerate genetic drift. To maintain the genetic health of the population, some degree of management would likely be necessary, monitoring lineages, possibly restricting certain pairings, potentially importing frozen genetic material to introduce diversity artificially. That word restricting deserves a moment of reflection. Reproduction is among the most intimate dimensions of human existence. The idea of a governing authority on a generation ship possessing the power to tell individuals who they may or may not have children with in the name of population genetic health is not a theoretical concern. It is a practical requirement for long-term biological viability, and it is the kind of requirement that breeds, in the most literal sense of the word, exactly the resentment and resistance that closed social systems cannot safely absorb. Consider also the transmission of knowledge. A generation ship requires expertise across an enormous range of disciplines simultaneously and continuously. Engineers who understand the propulsion system, the life support architecture, the reactor. Computer scientists who can maintain the software that controls every critical function. Medical professionals capable of handling injuries, illnesses, surgery, obstetrics, dental care, psychiatric treatment. Agricultural specialists who can diagnose and treat plant disease, manage soil chemistry, optimize yields in an artificial growing environment. teachers to educate each new generation, psychologists to support mental health, and on across every domain that a small, self-contained civilization requires. This knowledge must be preserved and transmitted without interruption across centuries. Any break in that chain, any generation that fails to adequately train successors in a critical area, any expertise that is taken for granted until it is suddenly needed and found to be absent, could be catastrophic. On Earth, knowledge has been lost repeatedly throughout history. The engineering principles behind Roman concrete were forgotten for over 1,000 years. The Library of Alexandria burned, and entire bodies of ancient scholarship vanished. Medieval Europe lost and laboriously rediscovered techniques that classical civilization had mastered. On Earth, lost knowledge can eventually be reconstructed, rediscovered, or imported from other cultures. On a generation ship, there are no other cultures. There is no outside library. There is no neighboring civilization to learn from. Lost expertise is simply gone, and what it sustained may fail before a replacement can be improvised. Religion and ideology introduce their own unpredictable dynamics. The founding crew may be secular scientists and engineers selected for technical competence and psychological stability, but human beings seek meaning. In the absence of the natural world, in the absence of the cultural context that normally provides frameworks of significance, in the face of confinement and mortality, and the existential weight of endless dark, religious and ideological movements arise. They have arisen in every human society that has ever existed, under every conceivable condition. There is no reason to believe a generation ship would be different. What happens when a religious movement emerges that rejects the mission, that interprets the journey as hubris, as transgression, as something to be repudiated? What happens when theological conviction comes into direct conflict with the operational requirements of the ship? History offers abundant evidence of what religious conflict does to societies. It tears them apart. It generates violence and persecution, and the kind of passionate division that rational argument cannot resolve. On Earth, religious conflict eventually exhausts itself or finds geographic separation as a partial solution. On a generation ship, there is no separation. The factions must coexist, indefinitely, in total proximity, with no release valve. None of this is speculation about edge cases. These are not unlikely failure modes. They are predictable consequences of placing human beings with the particular psychology, biology, social dynamics, and cultural tendencies that evolution gave us into an environment radically unlike the one we were shaped for durations far exceeding anything our minds and bodies were designed to sustain. We have never successfully maintained a small, fully isolated community in stable, functional condition for more than a few years. We have never come close. And the generation ship demands that we do it for centuries, in a far more demanding environment, with no outside assistance and no margin for failure. The universe does not grade on a curve. A generation ship that fails halfway between stars takes everyone aboard with it into the dark. Even if you could solve the social and psychological challenges, even if you could design a governance system that holds across centuries, maintain genetic diversity, preserve critical knowledge across generations, and keep a confined population mentally intact across the span of multiple human lifetimes, you would still face a set of purely physical problems that have nothing to do with human nature and everything to do with the brute arithmetic of keeping bodies alive in a hostile void. Start with food. A human being requires roughly 2,500 calories per day to maintain body weight and metabolic function under normal conditions. That translates to approximately 1 kilogram of food per person per day on a reasonably efficient diet. For a crew of 100 people on a 50-year journey, and 50 years gets you only to Proxima Centauri at 10% of light speed, the absolute nearest star, the arithmetic is straightforward. 100 people multiplied by 1 kilogram per day, multiplied by 365 days per year, multiplied by 50 years. The result is 1,825,000 kilograms of food, nearly 2,000 metric tons, assuming perfect preservation with zero spoilage, zero contamination, zero loss to equipment failure across half a century of continuous operation in space. That figure assumes you are traveling to the closest possible destination. For a star 10 light-years away, the food requirement more than doubles. For a star 50 light-years away, it becomes effectively incalculable as stored provisions. No ship could carry it. The mass alone would dwarf the vessel. This means you must grow food aboard the ship. There is no alternative. You need agricultural systems, hydroponic or aeroponic chambers where plants grow in nutrient-rich water or mist rather than soil, under artificial lighting tuned to the wavelengths that drive photosynthesis. You need pumps, sensors, climate control systems, nutrient delivery mechanisms, harvesting equipment. You need dedicated growing volume, potentially large sections of the ship given over entirely to plant cultivation. You need to pollinate crops, which normally happens through insects or wind, neither of which you can casually maintain in a spacecraft environment without introducing significant biological complexity. You need plant biologists who understand disease, who can identify fungal infections and bacterial blights before they propagate through your entire food supply. And if your crops fail, if a pathogen sweeps through your agricultural chambers, if a lighting system fails and a growing cycle is lost, if a contamination event destroys a season of production, you need reserves, enough stored food to survive the crisis, replant, and wait for the next harvest, which brings you back to stored provisions, which are mass, which costs energy to accelerate. Water is even more critical than food, and the arithmetic is even less forgiving. Human beings need approximately 2 to 3 liters of drinking water per day, but drinking is only the beginning. Hygiene requires water. Cooking requires water. Medical procedures require water. Growing food hydroponically requires enormous quantities of it, circulated continuously through root systems. Even in the most aggressively water-conservative scenario imaginable, a person aboard a spacecraft requires on the order of 50 liters per day when all uses are combined. For 100 people over 50 years, 100 multiplied by 50 liters, multiplied by 365 days, multiplied by 50 years, that is 91,250,000 liters. 91 million liters of water, weighing 91 million kilograms, or 91,000 metric tons. That is close to the total estimated mass of the ship itself. You cannot carry it, you must recycle it. Recycling water aboard a spacecraft is not a new concept. The International Space Station uses a sophisticated multi-stage filtration system that processes urine, sweat, and moisture from exhaled breath back into potable water. It recovers approximately 90% of the water that enters the system. The remaining 10% is lost to inefficiencies in filtration, to vapor that escapes before capture, to chemical processes that consume water without returning it. 10% sounds small, but on a 50-year voyage with 100 crew members, 10% annual loss against your total water inventory means a steady, irreversible depletion. You would need to carry buffer reserves to compensate, constantly improving recycling efficiency, approaching but never quite reaching the 100% recovery that thermodynamics ultimately prohibits. Perfect recycling is not an engineering challenge. It is a violation of physical law. There will always be loss. The question is only how much and how fast. Air presents the same structure of problem. Every person aboard exhales approximately 1 kilogram of carbon dioxide per day. In a sealed environment, CO2 accumulates rapidly, reaching toxic concentrations within hours without active removal. On Earth, the biosphere handles this through photosynthesis. Plants absorb CO2 and release oxygen in a cycle that has maintained breathable atmospheric composition for hundreds of millions of years. On a generation ship, you need mechanical systems to accomplish what the entire living surface of a planet accomplishes naturally. The International Space Station uses a carbon dioxide removal assembly that scrubs CO2 from cabin air through chemical absorption. The captured CO2 can then be processed through a Sabatier reactor, which combines it with hydrogen to produce water and methane. The water re-enters the station's water supply. The methane is typically vented. The hydrogen needed for the reaction is recovered through electrolysis, splitting water molecules into hydrogen and oxygen using electrical current. with the oxygen returning to the cabin atmosphere. This creates a partial cycle, not a complete one. Energy is required at every step. Consumable reagents are required at every step. Equipment degrades and must be maintained. And the system is not perfectly efficient. Some oxygen is lost in the process. Some CO2 is not fully captured. Some hydrogen escapes before it can be recombined. These small inefficiencies, accumulated across decades, erode your reserves. The only way to approach something resembling a genuinely closed life support cycle is through biology. Plants, growing in your agricultural chambers, absorb CO2 and release oxygen through photosynthesis. They process water through their root systems and release it as vapor through transpiration. They produce food. A well-designed biological life support system, sometimes called a bioregenerative system in principle, allows food production, air recycling, and water recycling to reinforce each other in something approaching a stable loop. We know this is theoretically possible because Earth itself is proof. The biosphere has maintained stable atmospheric chemistry, liquid water, and biological productivity across billions of years through exactly this kind of interconnected cycling. But Earth's biosphere had billions of years and the entire surface of a planet to develop those stable equilibria. We are trying to replicate that stability on a compressed scale in an artificial environment from scratch within years and then maintain it without deviation for decades or centuries. The most serious attempt to test closed ecological life support on a meaningful scale was Biosphere 2, constructed in the Arizona desert in the late 1980s. The facility enclosed 3.14 acres under glass, including artificial rainforest, ocean, savanna, and agricultural zones. 8 researchers sealed themselves inside in 1991 for a planned 2-year experiment in self-sufficient living. It failed. Oxygen levels inside the structure dropped steadily over the first year, from the 21% that characterizes Earth's atmosphere to levels approaching 14%, comparable to conditions at high altitude, causing headaches, fatigue, and impaired cognitive function in the crew. The cause was eventually traced to soil microbes consuming oxygen faster than the plants could replace it. The experiment required outside intervention to pump supplemental oxygen into the facility. Food production proved insufficient to fully feed the crew, requiring the use of stored reserves. Certain species thrived beyond expectation and disrupted the balance of the ecosystem. Others declined and disappeared. The carefully designed equilibrium of the biosphere unraveled in ways the designers had not anticipated and could not fully control. And Biosphere 2 had advantages that a generation ship would not. It received natural sunlight through its glass panels. It sat within Earth's gravity field. External researchers could monitor every parameter and intervene immediately when problems emerged. The crew could be resupplied or evacuated if necessary. The experiment lasted 2 years before it was effectively abandoned. A generation ship would need to maintain a stable, closed ecosystem for 50 years, or 100, or more, in the absence of natural sunlight, in microgravity or artificial gravity, with no possibility of external intervention, with no resupply, with no evacuation option. The honest assessment, informed by everything we know about ecological systems and bioregenerative life support, is that we do not know how to do this. We may not be able to do this. The technical challenges are not merely formidable, they may exceed what is physically achievable within the constraints imposed by mass, energy, and the inherent instability of small closed ecosystems over long time periods. And then, layered over all of this, is the threat that receives less attention than it deserves. Perhaps because it is invisible, perhaps because it operates slowly, accumulating damage that manifests as illness or cognitive decline or death years after the exposure occurred. Radiation. Space is not merely empty, it is saturated with radiation from multiple sources, each presenting its own profile of danger, and together constituting an environment that the human body was not designed to survive in for extended periods. The first source is the Sunday. Our star emits a continuous stream of charged particles, protons, and electrons called the solar wind. This stream flows outward through the entire solar system at several hundred kilometers per second. Near Earth, the planet's magnetic field deflects most of these particles away from the surface, funneling them toward the poles where they produce the auroras. In deep space between stars, there is no planetary magnetic field. You are exposed directly. More dangerous than the steady solar wind are the sudden, intense eruptions called solar flares and coronal mass ejections. During these events, the Sun releases surges of high-energy particles, primarily protons, that can increase radiation flux by orders of magnitude over periods of minutes to hours. Astronauts aboard the International Space Station receive advance warning of major solar events and take shelter in the station's most heavily shielded sections. A spacecraft in interplanetary space, let alone interstellar space, has no planet to hide behind and no magnetosphere to provide protection. A major solar particle event could deliver a lethal radiation dose to an exposed crew within hours. The second source is galactic cosmic rays. These are high-energy particles, mostly protons, but also the nuclei of heavier elements accelerated to velocities approaching light speed by the shock waves of supernova explosions and other violent processes distributed throughout the galaxy. Cosmic rays carry extraordinary energy. Individual particles have been detected with kinetic energies equivalent to a baseball thrown at moderate speed, concentrated into a single subatomic particle. When a cosmic ray particle strikes matter, it does not simply deposit energy the way lower energy radiation does. It shatters atomic nuclei, producing cascades of secondary particles, a shower of radiation from a single initial impact. If that shower passes through biological tissue, it leaves a trail of broken molecular bonds, fragmented DNA strands, ionized atoms. If the damage occurs in a cell's genetic material and is not repaired correctly by the cell's repair mechanisms, which handle ordinary radiation damage competently but struggle with the complex, clustered damage that cosmic ray secondaries produce, the cell may malfunction, die, or become cancerous. We know with certainty that long-duration spaceflight increases cancer risk. Studies of astronauts who spent months aboard the International Space Station document measurable increases in cancer incidence in the years following their missions. And those astronauts were still relatively close to Earth, still partially protected by the planet's magnetic field, and their exposures lasted months rather than decades. A crew spending 40 or 50 years in interstellar space beyond any stellar magnetosphere, exposed to the full flux of galactic cosmic rays from every direction, would accumulate radiation doses that current models suggest would be severely harmful and possibly fatal well before the journey's end. The obvious response is shielding. Build thicker walls. Surround the crew compartments with material dense enough to stop incoming particles. And shielding does help to a point. Water is an effective radiation shield. A meter of water stops most lower energy radiation and meaningfully reduces cosmic ray flux. But a cubic meter of water weighs 1,000 kilograms. Surrounding a habitable section of a spacecraft with even a modest layer of water shielding on all surfaces adds hundreds of thousands of kilograms to the ship's mass, which requires more energy to accelerate, which requires more fuel, which adds more mass, which requires still more energy, in the recursive spiral that the rocket equation makes familiar. Lead, the classical radiation shielding material, is denser than water and even heavier per unit volume. Aluminum provides some protection, but requires greater thickness. Every shielding material capable of meaningfully attenuating cosmic ray flux comes with a mass penalty that compounds the propulsion problem catastrophically. Some engineering proposals suggest using electromagnetic fields to deflect incoming charged particles, creating an artificial magnetosphere around the spacecraft analogous to Earth's own protective envelope. This approach has theoretical merit. Magnetic fields add no significant mass and would deflect the protons and heavier nuclei that constitute most cosmic ray flux. But generating a magnetic field strong enough to deflect particles traveling at nearly light speed requires superconducting electromagnets, power systems capable of sustaining them continuously for decades, cooling infrastructure, and redundant backups for every component. All of that is equipment. Equipment has mass. and magnetic fields deflect only charged particles. Neutrons, which are produced when cosmic rays collide with shielding material, carry no charge and pass through magnetic fields unimpeded. Gamma rays, which are high-energy photons rather than particles, also ignore magnetic fields entirely. An electromagnetic shielding system would need to be supplemented by physical shielding against these uncharged forms of radiation, which returns you to the mass problem. Beyond the biological hazard, radiation degrades the electronics that keep the ship alive. High-energy particles passing through semiconductor devices can flip individual bits in memory, a phenomenon called a single-event upset, causing data corruption, software errors, or hardware damage. Over years and decades of exposure, cumulative radiation damage degrades the performance of processors, sensors, and control systems. Spacecraft electronics are designed with radiation hardening in mind, but hardening has limits, and those limits are calibrated for mission durations of years, not decades. Critical navigation computers, life support controllers, and communication systems exposed to cosmic ray flux for half a century would require replacement components that must be carried aboard, maintained without degradation, and installed by crew members with the technical expertise to do so correctly, expertise that must itself be preserved across generations. The radiation environment is not a problem that better engineering will solve cleanly. It is a fundamental feature of interstellar space, a consequence of the violent astrophysical processes that fill the galaxy with high-energy particles, and the human body, shaped by billions of years of evolution under the protection of a planetary atmosphere and magnetic field, has no natural defenses against it. We are creatures of a sheltered world. Step beyond that shelter for long enough, and the universe makes clear that it did not design this environment with us in mind. 8:49 分. There is one more physical hazard that deserves careful attention before we move beyond the purely mechanical challenges of interstellar travel. It is a hazard that sounds almost absurd when stated plainly, because in our ordinary experience, it is not a hazard at all. It is simply the stuff that fills space. Dust, gas, the sparse material that drifts between the stars. In everyday terms, interstellar space is extraordinarily empty. The average density of matter in the space between stellar systems is roughly 1 hydrogen atom per cubic centimeter. To put that in perspective, the air you are breathing right now contains approximately 27 billion molecules per cubic centimeter. Interstellar space, by comparison, is a vacuum so profound that the best laboratory equipment on Earth cannot replicate it. If you could somehow transport a cubic meter of interstellar medium to a laboratory, it would register as essentially nothing. At the speeds we have been considering, however, that apparent emptiness becomes something else entirely. At 10% of light speed, 30,000 kilometers per second, a spacecraft is not moving through space the way a ship moves through water, gently pushing fluid aside as it passes. It is striking every particle in its path, with kinetic energy determined by the mass of the particle and the square of the velocity. And the velocity is 30,000 kilometers every second. A single gram of dust, one paperclip's worth of material striking your ship at 10% of light speed, carries kinetic energy equivalent to roughly 22 kilograms of high explosive detonating on impact. Not at the surface, on impact, instantly. Punching through your hull, destroying whatever lies behind it, potentially breaching the pressure seal that keeps the air inside and the vacuum outside. Interstellar space contains not just hydrogen atoms, but dust grains, tiny particles of silicate and carbon compounds, ranging from fractions of a micrometer to perhaps a millimeter across. The density is low, but at 30,000 kilometers per second, your ship sweeps through an enormous volume of space every second, and the cumulative probability of encountering even a small dust grain over a journey lasting decades is not negligible. It approaches certainty. Some engineering proposals address this with a shield mounted at the ship's forward end, a sacrificial structure of dense material designed to absorb impacts before they reach the inhabited sections. Project Daedalus, the British Interplanetary Society's fusion probe study from the 1970s, included a beryllium shield on its leading face for exactly this reason. but a shield capable of protecting a large crewed vessel from hypervelocity impacts across 4 decades of travel would itself be enormously massive. Adding to the propulsion problem we have already established is nearly insurmountable. Even the hydrogen atoms, individually negligible, become a collective obstacle at relativistic speeds. Traveling at 10% of light speed through a medium containing 1 hydrogen atom per cubic centimeter, your ship encounters roughly 3 trillion hydrogen atoms per second per square meter of forward-facing surface. Each collision is individually tiny, but the cumulative effect is a form of drag, a continuous resistance that slows the ship and heats the forward surfaces through friction. Over decades, this erosion would degrade unprotected surfaces, potentially compromising systems mounted at the ship's front. You would need to account for it in your propulsion calculations and protect exposed components accordingly, again adding mass and complexity. At higher speeds, the problem intensifies dramatically. At 50% of light speed, a hydrogen atom strikes with 25 times the kinetic energy it carries at 10%. At 90%, the relativistic math pushes the energy higher still. The interstellar medium that is irrelevant at planetary travel speeds becomes a genuine structural threat at the velocities that would make interstellar journeys feasible within a human lifetime. Detection and avoidance offer only partial solutions. At 10% of light speed, your ship covers 30 kilometers every millisecond. A dust grain detected a kilometer ahead gives you roughly 30 microseconds to react, to process the detection, calculate a course correction, fire maneuvering thrusters, and actually move the ship far enough to avoid the impact. The reaction time required is shorter than the fastest electronic systems can operate, let alone human reflexes. You would need autonomous collision avoidance systems capable of detecting hazards at ranges of thousands of kilometers and executing evasive maneuvers continuously throughout the voyage, running without interruption for decades, never experiencing a critical software failure or sensor degradation that allowed a lethal impact through. This is not impossible in principle, but it is another layer of complexity, another system that must function perfectly across 50 or 100 years, another point of failure in an architecture that already has far too many. Now we arrive at something stranger, something that sounds like science fiction but is, in fact, among the most rigorously verified predictions in all of physics. At a significant fraction of light speed, not just 10%, but 50, 70, 90%, and above, the universe stops behaving the way intuition suggests it should. The equations that govern motion at ordinary velocities, the mechanics that Newton formulated in the 17th century and that serve us perfectly well for everything from billiard balls to spacecraft in our solar system, quietly break down. In their place, the framework that Einstein completed in 1905, special relativity, takes over. And special relativity contains a prediction so counterintuitive that it remains difficult to accept even after a century of experimental confirmation. Time is not constant. For an object moving relative to a stationary observer, time passes more slowly, not as a metaphor, not as a perceptual illusion, but as a measurable physical reality. Clocks on a moving spacecraft tick more slowly than clocks on Earth, by precisely the amount that Einstein's equations predict, verified repeatedly by atomic clocks aboard aircraft, confirmed by the behavior of particles in accelerators, built into the corrections that make GPS satellites function accurately. Time dilation is not theoretical. It is measured daily by technology that billions of people use without knowing it. The quantity that describes this effect is called the Lorentz factor, often denoted by the Greek letter gamma. At 10% of light speed, gamma is approximately 1.005 time, passes about 0.5% more slowly aboard the ship than on Earth, a barely perceptible difference. At 50% of light speed, gamma rises to roughly 1.15 time, passes about 15% more slowly. At 90%, gamma reaches approximately 2.3. At 99%, it climbs to just over 7. At 99.9%, it exceeds 22. What this means in practice: a ship traveling at 99% of light speed toward a star 50 light-years away would, from Earth's perspective, take just over 50 years to complete the journey. But the crew aboard would experience only about 7 years. They would arrive having aged 7 years while Earth aged 50. They would be the same age they were when they left, give or take. The people they knew on Earth would be 50 years older. Many would be gone. If they somehow returned another 50 light years back to Earth at the same speed, they would arrive 100 years after departure, having aged only 14 years. Everyone they had known would almost certainly be dead. Their children, if they had left any behind, would be elderly or gone. The language might have shifted. The political structures they grew up under would have transformed beyond recognition. The technology would be unrecognizable. They would be strangers not just in space, but in time. This is not a problem that can be engineered around. It is a consequence of the geometry of space-time, as fundamental as the fact that parallel lines do not meet. Travel fast enough to make interstellar journeys survivable in terms of crew lifetime, and you sever the connection to everything the crew left behind, not as a side effect, as a mathematical certainty. Communication compounds the isolation. Radio signals travel at light speed, the fastest possible rate for any signal. A message sent from a ship 50 light years from Earth takes 50 years to arrive. A reply takes 50 years to return. A single exchange of information spans a century. By the time the crew receives an answer to a question, the person who answered it has almost certainly died. The civilization that composed the response has moved on through 50 years of history. The conversation is not a conversation in any meaningful sense. It is an exchange of messages across time between people who share a language but no longer share a world. Interstellar colonists would not merely be physically distant from humanity. They would be temporally isolated from it, embedded in a different slice of time, unable to participate in the ongoing life of the civilization that sent them. They would be alone in a way that no explorer in human history has ever been alone, because no previous explorer was separated from home not just by distance, but by the irreversible flow of years. But let us grant all of this. Let us imagine that every obstacle has been overcome, energy problem solved, life support perfected, social structures maintained against all historical precedent, radiation managed, dust shielded, relativistic effects accepted. The ship arrives, battered and transformed by its journey, at a distant star system. What does it find? The honest answer, informed by everything planetary science and exoplanet research has revealed over the past 3 decades, is that the most likely outcome is disappointment. Habitable planets, worlds with liquid water on their surfaces, stable climates, breathable atmospheres, protection from stellar radiation, and conditions that support the biology Earth life requires are not common. They may not be rare by cosmic standards, but they are far from guaranteed in any given star system. NASA's Kepler Space Telescope, which monitored over 150,000 stars for the transit signatures of orbiting planets, confirmed thousands of exoplanets and revealed that planetary systems are indeed common throughout the galaxy. But the vast majority of those planets are not Earth-like. Most detected exoplanets are gas giants, Jupiter-scale worlds of hydrogen and helium with no solid surface to stand on. Many orbit so close to their stars that they are tidally locked, one face permanently turned toward the star in perpetual scorching daylight, the other frozen in permanent night. Many orbit stars that are far more violent than our sun-red dwarfs, which are the most common stellar type in the galaxy, are prone to intense flares that bathe nearby planets in bursts of ultraviolet and X-ray radiation, powerful enough to strip away atmospheres over geological timescales and sterilize exposed surfaces. Many planetary orbits are too elliptical for stable temperatures. Many systems contain multiple stars, whose gravitational interactions render planetary orbits chaotic over long periods. Even a planet that checks every box from a distance, right size, right temperature, rocky surface, in the habitable zone of a stable star, might be completely uninhabitable upon arrival. Its atmosphere might be thick with carbon dioxide, like Venus, creating a runaway greenhouse effect that raises surface temperatures to the point where lead flows as liquid. It might lack a magnetic field, leaving its surface exposed to direct stellar wind erosion and radiation. It might be geologically inert, lacking the plate tectonics that on Earth regulate atmospheric composition and recycle carbon over millions of years. It might be tidally locked, with a climate so extreme between its permanent day and permanent night sides that the in-between terminator zone, the only potentially habitable strip, is vanishingly small and subject to violent atmospheric dynamics. It might already harbor life. That possibility, which would represent one of the most extraordinary discoveries in human history if encountered from the safe distance of a telescope, becomes a profound ethical and practical crisis. If you arrive in person aboard a ship carrying thousands of Earth organisms intentionally in the crew, unintentionally in the microscopic passengers that hitchhike on every surface of every human body and every piece of equipment, introducing Earth biology into a living alien ecosystem could devastate whatever native life exists, in the same way that introduced species have driven extinctions across Earth's own ecosystems whenever biological communities that evolved in isolation were brought into contact. Or conversely, alien biochemistry might be toxic to Earth life in ways that cannot be predicted or protected against in advance. We cannot know what we will find until we arrive. And if we arrive and find that the destination is uninhabitable through atmospheric chemistry, radiation exposure, toxic biology, geological instability, or any of a dozen other failure modes, we have no recourse. We cannot call for help, we cannot resupply, we cannot try a different planet in the same system if it proves unsuitable, because our resources are exhausted by the journey itself. We are committed, completely and irreversibly, to making it work with what we have on a world that may be actively hostile to our presence. And even in the best imaginable case, a genuinely Earth-like planet with breathable air and liquid water and no competing biology, the work of establishing a self-sustaining presence from scratch on an alien world, using only the equipment carried across light years, with no possibility of resupply or rescue, would be the most demanding survival challenge in human history. Different gravity affecting every physical process the crew has adapted to. Different day length, disrupting biological rhythms calibrated to Earth's 24-hour cycle. Different atmospheric pressure and composition requiring continuous adjustment. Soil chemistry incompatible with Earth agriculture until it can be amended and cultivated across many growing seasons. No existing infrastructure of any kind. No roads. No shelter beyond what is constructed. No established food systems. No medical supply chains. No communication networks. The colony would be, from its first moment, entirely dependent on its own resources and expertise to survive. And those resources would have been stretched across decades of travel before ever touching the new world's surface. The stars are distant, the journey is brutal, and the destination offers no guarantees. At this point in the conversation, a particular kind of resistance tends to arise. It is understandable. It is deeply human. You have heard the problems, the energy requirements, the life support challenges, the radiation, the social collapse, the navigational hazards, the uncertain destinations, and some part of you refuses to accept that these obstacles are truly insurmountable. Because we have a century of stories telling us otherwise. Because science fiction has spent 100 years populating our imaginations with technologies that dissolve these barriers as casually as a hand waving away smoke. Warp drives, wormholes, hyperspace, subspace, jump drives, fold technology. The names vary across franchises and novels and films, but the function is always the same, a mechanism that circumvents the tyranny of interstellar distance, that allows ships to cross light years in days or weeks, that makes the galaxy traversable on a human timescale. The question worth asking, seriously worth examining without the comfort of narrative convenience, is whether any of these concepts have genuine grounding in the physics we actually understand, not whether they make compelling stories, whether they are real possibilities that current science leaves open, or whether they are, at their core, storytelling devices with no more physical basis than a magic spell. Begin with the warp drive, because it is the concept with the most legitimate scientific pedigree. In 1994, a Mexican physicist named Miguel Alcubierre published a paper in the journal Classical and Quantum Gravity, presenting a mathematical solution to Einstein's field equations, the equations that govern the curvature of spacetime, that appeared, at first glance, to permit faster-than-light travel without violating relativity's core prohibition. The concept is elegant. Rather than accelerating a spacecraft through space, which relativity forbids beyond light speed for any object with mass, the Alcubierre drive would manipulate space itself. It would compress the fabric of spacetime in front of the ship and expand it behind, creating a wave in spacetime geometry that carries the ship forward the way a surfer is carried by a wave of water. The ship itself would not be moving through local space at all. It would be sitting still inside a bubble of flat spacetime, while the bubble and everything in it was transported by the deformation of the surrounding geometry. The mathematics, within the framework of general relativity, are internally consistent. Alcubierre's solution does not obviously break any of the equations, and that is precisely what made the paper extraordinary when it was published, and what has kept it in scientific discussion in the 3 decades since. But the physics required to actually construct such a drive reveal why it remains entirely theoretical and almost certainly impossible. The first requirement is matter with negative mass energy density, not antimatter. Antimatter has positive mass and behaves gravitationally like ordinary matter, falling toward other matter rather than away from it. What the Alcubierre metric requires is something fundamentally different, a form of matter or energy that gravitationally repels, that curves spacetime in the opposite direction from ordinary positive energy matter. Physicists call this exotic matter. It is not a substance we have discovered, synthesized, or observed. It may not exist at all. Quantum field theory does permit certain configurations of quantum fields to have negative energy density in limited regions, the Casimir effect, which produces a measurable attractive force between closely spaced metal plates in a vacuum, is a laboratory-confirmed example of negative energy density on microscopic scales. But whether negative energy density can be made to exist in the macroscopic quantities and geometric configurations that an Alcubierre drive would require is entirely unknown, and theoretical analysis suggests the answer is almost certainly no. The second problem is scale. Early calculations of the energy required to generate an Alcubierre warp bubble around even a small spacecraft produced numbers that beg a description. Harold White at NASA's Johnson Space Center spent years attempting to find geometric configurations of the warp field that might reduce the energy requirement, and his work did identify mathematical adjustments that brought the theoretical energy cost down significantly from the original estimates. But even the most optimistic revised figures require negative energy on a scale that exceeds anything achievable with any physical process we understand. Some analyses suggest the energy equivalent of a mass larger than the observable universe. Others, more charitable to the concept, suggest something closer to the mass of Jupiter. Neither figure is accessible with any technology we can envision. The third problem is causality, and it is perhaps the deepest of all. Faster-than-light travel, regardless of the mechanism, regardless of whether it is achieved by accelerating through space or by warping space or by any other means, creates situations in which the causal structure of the universe breaks down. In the framework of special relativity, events that are separated by a space-like interval, meaning they are too far apart for light to travel between them in the available time, have no fixed temporal order. Different observers, moving at different velocities, will disagree about which event happened first. This is not a measurement error, it is a fundamental feature of how space-time works. When you combine this with faster-than-light travel, the consequence is that a sufficiently sophisticated arrangement of faster-than-light journeys would allow you to arrive at a destination before you departed. Not before you departed from the perspective of some particular reference frame, before you departed from any reference frame. Cause preceding effect, not as a philosophical puzzle but as a literal physical outcome. The universe appears to prohibit this. The apparent prohibition is so robust and so deeply embedded in the structure of relativistic physics that most theoretical physicists treat it as a genuine law rather than a gap in understanding. And if faster-than-light travel creates time travel paradoxes, the laws of physics almost certainly forbid it, because a universe in which effects precede causes is not a universe in which physics can have consistent rules at all. Traversable wormholes face a nearly identical set of objections. The concept has roots in genuine physics. Einstein and Nathan Rosen identified solutions to the field equations of general relativity in 1935 that described what we now call Einstein-Rosen bridges connections between distant regions of spacetime through a tunnel-like structure that shortcuts the path between them. The popular name wormhole was coined later, and the concept has been explored seriously by physicists including Kip Thorne, who in the 1980s examined whether a traversable wormhole, one that a physical object could pass through without being destroyed, was compatible with general relativity. Thorne's analysis concluded that traversable wormholes are mathematically possible within general relativity, but that keeping them open and stable against the tendency of the wormhole throat to collapse requires threading it with exotic matter, the same negative energy density substance that the Alcubierre drive demands. The mouth of a traversable wormhole would pinch shut unless propped open by something that gravitationally repels the collapsing geometry, and exotic matter, as we have already established, is either extraordinarily difficult to produce in meaningful quantities or physically impossible to produce at all. Beyond the exotic matter problem, stabilizing a wormhole mouth against the quantum effects that would, according to most theoretical analyses, cause it to catastrophically amplify radiation until it destroyed itself, a phenomenon called the Hawking-Thorne-Preskill controversy, related to what happens to quantum fields near closed time-like curves, represents an unsolved problem that many physicists believe has no solution, consistent with both general relativity and quantum mechanics. And again, traversable wormholes like warp drives are potential mechanisms for faster than light travel, and faster than light travel creates causality violations. The universe's apparent prohibition on time paradoxes likely extends to wormholes as well. Hyperspace, subspace, and the various other extra-dimensional shortcuts that populate science fiction have essentially no grounding in physics at all. String theory and its relatives do posit the existence of extra-spatial dimensions beyond the three we experience. But these extra dimensions, in the theoretical frameworks where they appear, are either compactified, curled up at scales so small that they cannot be traversed by macroscopic objects, or they are accessible only through physics that operates at energies the universe has not seen since the first fractions of a second after the Big Bang. The notion that a spacecraft could somehow enter a parallel dimension where distances are shorter and travel faster than light is a narrative device, not a physical theory. There is no mathematical framework suggesting it is possible, and no experimental observation hinting it might be real. The speed of light is not a record waiting to be broken. It is not an arbitrary speed limit imposed by engineering limitations that future technology will lift. It is a consequence of the geometry of space-time, the relationship between space and time that is built into the structure of reality at the most fundamental level. In a universe governed by special relativity, which our universe demonstrably is, the speed of light is the conversion factor between spatial and temporal dimensions. It is as fundamental as the existence of space and time themselves. Nothing with mass reaches it, nothing exceeds it, not because we have not yet figured out how, but because the universe's own geometry does not permit it. Some people, confronted with the impossibility of crude interstellar travel, redirect toward a different vision. Not humans among the stars, but machines. Self-replicating automated probes, a concept named after the mathematician John von Neumann, who first analyzed the theoretical possibility of self-reproducing machines that could spread through the galaxy over millions of years without the biological and social constraints that make human interstellar travel so intractable. The concept is this: launch a probe toward a nearby star system. When it arrives, it mines raw materials from asteroids or other available bodies, uses those materials to fabricate copies of itself, and launches those copies toward other star systems. Each copy does the same upon arrival. The process is exponential. In principle, a single initial probe could seed thousands of daughter probes within a few generations, tens of thousands within a few more, and within a few million years, a blink of geological time von Neumann probes could have visited every star system in the galaxy, even at velocities far below the speed of light. The mathematics of exponential replication suggest that a civilization capable of building such probes could survey the entire Milky Way within 10 to 100 million years. Given that the galaxy is approximately 13 billion years old, any civilization that developed this technology more than 100 million years ago, a small fraction of the galaxy's history, should have probes in virtually every star system by now. That observation feeds directly into one of the deepest puzzles in all of science, which we will return to shortly. But as a solution to the problem of interstellar travel, von Neumann probes have their own profound difficulties. We do not know how to build self-replicating machines. Not in the sense that we lack a specific engineering detail. We lack the entire conceptual framework for designing a machine that can identify arbitrary raw materials in an alien star system, extract and process them, fabricate precise copies of its own complex internal architecture, and launch those copies successfully, all without human oversight and with no possibility of intervention if something goes wrong. The engineering challenge is not incremental. It is categorical. Even granting that such machines could be built, maintaining reliable behavior over the timescales involved strains credibility. A probe operating autonomously for thousands of years, replicating across hundreds of generations in environments its designers never encountered, would be subject to copying errors, the mechanical equivalent of genetic mutation. Small deviations accumulate. After enough generations, the machines might behave in ways their original designers never intended. A self-replicating machine that malfunctions and begins consuming resources indiscriminately. An idea that physicists and science fiction writers have both explored under the name the Grey Goo problem or the Berserker scenario, would be extraordinarily difficult to stop, given that any corrective signal from the originating civilization would take thousands of years to arrive. And von Neumann probes, however sophisticated, do not solve the fundamental problem. They are machines. They can gather data and transmit it home across light years. They can confirm the existence of planets, analyze their atmospheres, map their surfaces, perhaps even confirm the presence of life. But the data arrives as signals, not as experience. The humans who receive it are still confined to their home system. The probes explore on our behalf, but we do not go with them. The dream standing on another world, breathing alien air, building a civilization among the stars, remains unrealized. The universe does not appear to offer a shortcut. Every path that human ingenuity has proposed, every warp bubble and wormhole and self-replicating machine and hyperspace corridor dissolves on contact with the actual physics of the cosmos. Not because we have failed to be clever enough, because the rules of the universe do not include a provision for the thing we want. There is a question that has haunted astronomy since the middle of the 20th century. It was posed informally by the physicist Enrico Fermi during a lunch conversation at Los Alamos in 1950, though the idea had been circulating in various forms for years before he gave it its famous expression. The question is simple enough to state in a single sentence: where is everyone? The universe is approximately 13.8 billion years old. Our galaxy alone contains somewhere between 200 and 400 billion stars. The exoplanet surveys conducted by Kepler, TESS, and ground-based observatories over the past 3 decades have established beyond reasonable doubt that planetary systems are common, that the majority of stars host planets, and that rocky planets in or near habitable zones exist in the billions across the Milky Way alone. Given these numbers, given the sheer abundance of potentially life-supporting worlds, and the immense span of time available for life to emerge and civilizations to develop, the expectation that we should be surrounded by evidence of other intelligent species' radio signals, engineering on stellar scales, the signatures of civilizations that have been expanding for millions of years seems not merely reasonable, but almost mathematically inevitable. And yet, silence, in every direction, at every frequency, across every instrument we have ever pointed at the sky. No signals, no megastructures, no evidence of any kind that intelligence has emerged anywhere other than on this one small world orbiting an unremarkable star in the outer regions of an ordinary spiral galaxy. This contradiction, the vast improbability of cosmic silence given the apparent abundance of cosmic opportunity, is what astronomers call the Fermi paradox, and the proposed solutions to it are, without exception, disturbing. One family of solutions suggests that life is simply far rarer than the raw numbers imply, that the emergence of life from chemistry, or the transition from simple microbial life to complex multicellular organisms, or the development of intelligence and technology, requires a sequence of improbable steps, so unlikely that the expected number of civilizations in the observable universe is very small, perhaps close to one, perhaps exactly one. Perhaps we are not merely unusual. Perhaps we are unique, the sole instance of consciousness in a cosmos containing 2 trillion galaxies. The rare Earth hypothesis, developed most fully by the paleontologist Peter Ward and the astronomer Joe Kirschvink, argues that the particular combination of conditions that made Earth habitable, the right kind of star, the right position in the galaxy, the right planetary configuration, the right geological history, the right series of mass extinctions and recoveries that shaped the trajectory of evolution, is so improbable that its replication elsewhere is vanishingly unlikely. If this is true, the Fermi paradox dissolves. The universe is silent because it is, for all practical purposes, empty of minds. Another family of solutions acknowledges that civilizations likely do arise, but proposes that something destroys or limits them before they can spread across the galaxy. This is the concept of the Great Filter, a barrier so formidable that virtually no civilization crosses it. The disturbing question embedded in the Great Filter hypothesis is whether the filter lies behind us or ahead. If the filter is behind us, if the improbable step was in our past, perhaps the emergence of the eukaryotic cell, or the transition from single cell to multicellular life, or the development of language and abstract thought, then we may have already passed through the most dangerous bottleneck. We may be among the first complex civilizations to emerge in the galaxy, not because life is rare, but because the timing required for our particular sequence of biological developments is unusual. In that case, the future may be open. The silence around us is the silence of a galaxy that has not yet had time to fill with minds. But if the filter lies ahead, if there is something that civilizations at approximately our stage of development consistently fail to survive, then the silence takes on a different quality. It becomes a warning. Every direction we look and find nothing is another data point suggesting that the thing which ends civilizations is common, reliable, and waiting. What could such a filter be? Nuclear war, ecological collapse, the development of artificial intelligence that supersedes and replaces biological intelligence, resource depletion, pandemic, the simple thermodynamic exhaustion that comes from building industrial civilization on a finite world. Any of these, if they reliably terminate civilizations before they develop the capacity for genuine interstellar communication, would explain the silence. And then there is a third possibility, one that is quieter than the others, less dramatic, but in some ways more profound. Perhaps the filter is not a catastrophe. Perhaps it is simply physics. Perhaps every civilization that reaches our level of technological sophistication looks outward, does the mathematics we have been doing throughout this conversation, and arrives at the same conclusion: the energy requirements are impossible. The travel times exceed biological lifespans by orders of magnitude. The life support challenges have no clean solution. The social structures required cannot be maintained. The physics does not permit the shortcuts. And so they stay, confined to their home star system, not by disaster or self-destruction, but by the simple, immovable fact that the universe built distances too large for the creatures it produced. If this is true, the galaxy may be full of life, full of intelligence, full of civilizations that have been asking the same questions we ask, building the same mathematics, looking up at the same darkness, and reaching the same conclusions. Each one isolated on its own world, or at most its own star system, separated from every other by gulfs that no technology can bridge. Each one alone, not because it failed, but because the rules of the game make genuine connection impossible. There is something almost unbearable about that image, and something, if you sit with it long enough, that begins to feel like solidarity. Every mind in the cosmos, looking out at the same impossible distances, holding the same frustrated longing. We are not uniquely limited. We are, perhaps, typically limited. The universe treats all of its children the same way. We have now covered the full landscape of the problem. Chemical propulsion fails the arithmetic by factors of billions. Nuclear propulsion extends our reach, but not nearly far enough. Antimatter cannot be produced, stored, or used. Generation ships cannot be maintained against the full weight of human nature and biological reality over the timescales required. Radiation accumulates beyond any shielding solution that does not itself become prohibitively massive. The interstellar medium at relativistic speeds presents collision hazards that are difficult or impossible to manage. Relativistic time dilation severs the crew from the civilization that sent them. The destination offers no guarantees of habitability. Warp drives require exotic matter that does not exist. Wormholes require the same, and both create causality violations that physics appears to prohibit absolutely. Von Neumann probes are hypothetical machines we do not know how to build, and the speed of light is not a barrier to be broken but a feature of the universe's own geometry. The conclusion is not a failure of imagination. It is not a failure of ambition. It is not a temporary state that time and ingenuity will resolve. It is the universe speaking clearly, in the language of physics, about what it permits and what it does not. And here is where some people expect despair, where the weight of all these impossibilities seems to demand a kind of surrender, a dimming of wonder in the face of limitation. But consider what we have already done. We are collections of atoms, not special atoms, the same hydrogen and carbon and oxygen and nitrogen that fill the cosmos, forged in the interiors of stars that exhausted themselves and exploded billions of years before our sun was born. The calcium in your bones was manufactured in the core of a star that passed away more than 4 billion years ago. The iron in your blood was produced in a stellar death, so violent that it briefly outshone an entire galaxy. You are not merely connected to the universe in some poetic, abstract sense. You are made of it, literally, materially, chemically assembled from the debris of stellar lives that ended long before Earth existed. And somehow, through 4 billion years of chemistry becoming biology, biology becoming complexity, complexity becoming nervous systems becoming minds, that stellar debris became conscious, became curious, became capable of asking where it came from. We have measured the age of the universe to within a few tens of millions of years. We have mapped its large-scale structure, the web of galaxy filaments and voids that stretches across billions of light-years from our position on a small rocky world orbiting a minor star. We have detected gravitational waves produced by the collision of black holes more than 1 billion light-years away, confirming predictions that Einstein made with pencil and paper in 1916 before such measurements were conceivable. We have looked at the cosmic microwave background radiation, the afterglow of the Big Bang itself, the oldest light in the universe, and read in its patterns the story of the first few 100,000 years of cosmic history. We have sent spacecraft beyond the edge of our solar system. Voyager 1, launched in 1977, crossed into interstellar space in 2012 and continues transmitting from a distance of more than 23 billion kilometers so far that the radio signals it sends, traveling at the speed of light, take more than 22 hours to reach us. We have landed robots on Mars, flown a helicopter in Martian air, driven across Martian soil, analyzed the chemistry of Martian rocks looking for traces of ancient water and ancient life. We have dropped a probe through the atmosphere of Titan, Saturn's moon, and photographed its surface of hydrocarbon lakes and methane rain. We have flown past Pluto and seen its heart-shaped nitrogen glacier and its mountains of water ice rising from plains of frozen methane. We have discovered more than 5,000 confirmed planets orbiting other stars, with thousands more candidates awaiting confirmation. We have characterized the atmospheres of some of those planets, identifying the presence of water vapor, carbon dioxide, methane, and other compounds in the air of worlds dozens of light-years away, analyzed from Earth, using nothing but the spectrum of starlight filtered through those distant atmospheres. We have found planets in habitable zones. We have found planets smaller than Earth. We have found planets that rain iron, and planets with winds of several kilometers per second, and planets tidally locked to their stars in permanent day and night. We have understood our cosmic address with a precision that would have seemed supernatural to our ancestors. We know we occupy the third orbit of a G-type main sequence star, located roughly 26,000 light-years from the center of a barred spiral galaxy containing between 200 and 400 billion other stars. Itself one of approximately 2 trillion galaxies in the observable universe, all of it having emerged from a singularity of extraordinary density and temperature approximately 13.8 billion years ago. We know this from here, without going anywhere. Think carefully about what that means. The stars we cannot reach, we have nonetheless measured. The galaxies we will never visit, we have nonetheless mapped. The history of the cosmos before Earth existed, before life existed, before consciousness existed, we have nonetheless reconstructed it, working backward from observations made on a single pale world by creatures who have been technologically capable for the span of an eye blink in cosmic time. We cannot touch the stars, but we know them, and that distinction between touching and knowing, between physical presence and genuine understanding, is more important than it might initially appear. There is a philosophical tradition that equates knowledge with power, with the ability to act upon what is known. By that measure, knowledge of things we cannot reach might seem like a lesser form of knowing, impressive but ultimately hollow. But there is another way to think about it. Understanding the universe is not merely instrumental. It is not simply a means to the end of controlling or exploiting what we come to know. Understanding is valuable in itself. The act of comprehending a reality larger than yourself, of extending the reach of mind beyond the reach of hand, and of bearing witness to existence on a scale that dwarfs everything human, that is one of the most extraordinary things a conscious being can do. In a universe that appears to be mostly unconscious, mostly hydrogen and helium and dark matter, following physical laws with no one to observe or comprehend, the emergence of minds capable of understanding the whole is something remarkable, something that perhaps deserves to be taken seriously on its own terms, independent of whether those minds can also travel to the places they understand. We are the universe's way of knowing itself. That phrase sounds poetic, perhaps too poetic, but it is also literally true. The physical processes that govern stellar evolution, galactic dynamics, cosmological expansion, those processes have been operating since the Big Bang, with no observer, no comprehension, no meaning attached to them. The universe existed for approximately 9 billion years before Earth formed. For another 4 billion years, life existed on Earth, but had no capacity to understand the cosmos it was embedded in. Only in the last few thousand years, and only with real precision in the last few centuries, has any part of the universe developed the capacity to comprehend the rest of it. We are that part. This small, temporary, fragile arrangement of atoms on a minor world is the instrument through which the universe has, for the first time, become aware of itself. Perhaps that is enough. Perhaps it is more than enough. There is grief in accepting what we cannot have. The dream of standing beneath an alien sky, of watching 2 suns set over an ocean that no human eye has ever seen, of meeting minds that evolved in complete independence from our own, and finding in that encounter some reflection of what consciousness means in a cosmos this large. That dream has genuine beauty and genuine value, and it is not contemptible to mourn its impossibility. But there is also something clarifying about limitation, something that focuses attention on what remains. We cannot travel to the stars, and that will not change. But we have not yet mapped the deep ocean floors of Earth. We have not yet understood the full complexity of the human brain. We have not yet resolved the deepest questions in physics, the reconciliation of general relativity and quantum mechanics, the nature of dark matter and dark energy, the precise mechanism of consciousness itself. We have not yet searched every habitable world in our solar system for signs of life, the subsurface oceans of Europa and Enceladus, the ancient lake beds of Mars, the atmospheric chemistry of Venus. We have not yet listened to the full radio spectrum of the galaxy, with the sensitivity needed to detect civilizations like our own at interstellar distances. We have not yet been wise enough, for long enough, to deserve the universe we have. The solar system alone, this single star system that is all we will ever physically occupy, is vast beyond ordinary reckoning by human standards. 8 planets, more than 200 known moons, millions of asteroids in the main belt, billions of comets in the Oort cloud, stretching nearly a light year from the Sun in every direction. A region spanning several light hours across, containing more worlds and more environments than humanity could meaningfully explore in centuries of effort. There is no shortage of frontier here. There is no need to reach the stars to find new places, new challenges, new knowledge. And beyond our solar system, the universe remains fully open to the one form of exploration that physics permits us without restriction: the exploration of the mind, the exploration of the telescope. Every photon that reaches us from across the cosmos carries information about where it came from, about the temperature and composition and motion and age of the thing that emitted it. The universe is generous with its light. It broadcasts its nature in every direction continuously. We have only to build more sensitive instruments, to look more carefully, to interpret what we receive with greater sophistication. In the centuries ahead, we will characterize the atmospheres of Earth-like planets in neighboring star systems with spectroscopic precision sufficient to detect the chemical signatures of biology: oxygen produced by photosynthesis, methane generated by metabolism, the complex organic molecules that life on Earth produces in abundance. We may find those signatures. We may confirm, from a distance that no ship will ever cross in a human lifetime, that we are not alone. That life is not a local accident, but a cosmic phenomenon. That the universe, in its billions of years and its billions of worlds, has produced consciousness not once but many times. That confirmation, if it comes, will be among the most transformative moments in human history, not diminished by the distance that prevents us from meeting what we find, perhaps made more profound by it, knowing that other minds exist, separated from us by gulfs that cannot be bridged, each one looking out at the same darkness from its own island of light. That knowledge changes what it means to be here. It makes the universe inhabited in a way that it is not. So long as we believe ourselves alone, we will not shake hands with those minds. We will not share a meal or trade technologies or form alliances or conduct the face-to-face meeting that science fiction envisions. We will know they exist, and they, perhaps, will know we exist. And across the silence, across years and decades of signal travel time, we may exchange what conscious beings can exchange across such distances: mathematics, perhaps, music, the fingerprints of our respective understandings of a universe we share, but cannot cross together. That is not nothing. It may, in fact, be everything that the universe permits between minds that arose on separate worlds. We are small. That is simply true, and there is no softening it. A species that has existed for a few 100,000 years, on a planet that has existed for 4.5 billion years, orbiting a star that will burn for another 5 billion before it exhausts its fuel, in a galaxy that has been forming stars for nearly the age of the universe. In a cosmos so large that the light from its most distant reaches has been traveling since before Earth existed and has not yet arrived. By any measure, we are small, but we are also the thing that knows how small we are, and that is not small at all. The stars are not destinations we will reach. They are the furnaces that made us, that forged the atoms we are assembled from in the violence of nuclear fusion and the catastrophe of stellar death, and then scattered those atoms across space so that they could find each other again, here, on this world, in this arrangement, and become briefly capable of wonder. We carry the stars within us. In the carbon of our cells and the iron of our blood and the calcium of our bones, we are the residue of stellar lives that ended before our world began. We did not come from the stars in the sense of traveling from them. We came from them in the sense that matters more. We are made of them. We are their continuation, their consequence, their most improbable and most extraordinary product. And here we are, on this one world, beneath this one sky, looking out at distances we will never cross, understanding things we will never touch, bearing witness to a universe that spent nearly 14 billion years producing something capable of appreciating it. The warmth is here, the light is here, the consciousness that allows the cosmos to know itself is here, on this pale world, in this moment, which will not last forever and does not need to. It is extraordinary, it is temporary, and it is ours.